As far as your drawing projects, you will complete a variety of drawings and exercises designed to enforce correct dimensioning techniques. Both manual and CAD drawing techniques are employed. Enjoyed, actually, too. All drawings are turned in for evaluation. Now, we aren't going to do any dimensioning on here, just so you know, by CAD. Most of these assignments I give you, you will draw them on the appropriate template in CAD, print them, put them on a board, and then dimension by hand. Okay, that's in essence how we're going to do them. So you will have true size and shape and orthographic views to produce. Now you won't have to be redoing your geometry by hand, and that's just to speed things up a little bit. Please have your manual drawing tools here. You're going to get your first assignment tomorrow. Okay? Your first drawing assignment, I guess I should say. We'll do one final exam at the end of it. 3 weeks, 3 credits. We're not going to get 15 days for this course. Okay, normally 3 weeks would be 3 times 5, 15. We're going to be 3 weeks counting your Thanksgiving break, of which I think you folks are here next week, Monday, Tuesday, and then you're gone the last 3. So those will be part of this course, but we won't be lecturing on. Okay? So we're going to count that. So 3 weeks from today, in essence, we should be done. The text we'll be using is the Bertolini text. So this guy, our main drafting text. Chapters we're going to cover. 17 is the main one, dimensioning and tolerancing practices. We will jump into 19 as we're going to do some threaded fasteners. We're going to introduce those here, learn how to draw them due to standards, and also how to dimension them. Like I mentioned many times, I think in the past, we all have to know about nuts and bolts. We've got to do them, no matter what you do for a living. These things will be coming up. So that's what 19 is. We will not do all of 19. We will come back to it in drafting 150 and cover all of it. We're just going to get enough out of it right now to kind of make us dangerous. There is one other dimensioning chapter, chapter 18, which is geometric dimensioning and tolerancing. We will not be doing that chapter right now. That is specific to the mechanical engineering field. So therefore, we're going to wait till we hit drafting 150, which is the first course in the summer, and we will come back and hit chapter 18 during that time. But if you're not doing mechanical engineering, you don't really need GDT, if nobody else uses it except for those folks. Okay, so we're going to be focusing on 17. Fairly big chapter. There's a lot of stuff in here. We'll have no problem having material to go through. Nothing's changed as far as the grading policy and instructional policy. I'll try and be done by 10 each morning and running through. One thing on lectures. Tomorrow, if you wish, we have a chance for you to catch an extra lecture at about 1:20 to 1:30. The INL, I'm trying to finalize the time right now. The INL, the site, if you don't know about them, they're out by ARCO. They employ a lot of drafters, many of them in the Idaho Falls area, some of them on the site itself. The last time I looked, I think they had 60 plus drafters working for them. They're going to be in here talking to some folks, and they wanted to come talk to you folks about possible jobs and internships. And so I think their free time is 1:20 right now. I'm still kind of emailing the guy back and forth, see if we can work it. Gabe, I know that doesn't work for you. I don't know if you can, with a day's notice, get released from your high school and stay for that extra time or not. But you're welcome to if you can. So that will be going on tomorrow. I'll let you know as soon as I know a little bit more about it. Any questions on the syllabus? Okay, there is one other sheet on here. We're going to come back to this later. Just one other thing to kind of keep in mind that might pop up this semester. I'm trying to work this out where it doesn't go. I'll know more today, but I think some of you know I've kind of had some hand problems with carpal tunnel and stuff, and I've got to go get cut on. So I'm not sure when that's going to be. They tell me you're pretty much done for 3 days when you do that. So I'm trying to set it up so I kind of do it over our breaks, but I'm not sure that's going to work out. So I'm going to try and get a little bit ahead. I'm going to push pretty hard. So if I do have to miss a day or two for that, it won't influence how this class works. So I'm going to be pushing pretty hard for the next couple days. All right, let's talk about the transition of what we're doing here, okay? Because we're going to kind of take a move. The thing you want to know is right now we have been focusing on nothing but what we call the shape description of objects, how to draw things. And in fact, we've kind of gone over the tools. You can pretty much draw, at this point in time, anything that exists on the planet, following the rules that we have, and give true size and shape of these things to our construction folks, who then make us all money. Right? And that's kind of what we're in business for. So we've kind of done this, right? Where we've got our toolbox that's full, it's got our multi-views in it, orthographic projection, it's got our auxiliary views in it, it's got our sections in it. We've got all these different techniques that we use to describe stuff. Now the other thing we do, that's only half of our job, I guess really what I might try and say here. That's half of it. Is we have to do two things. We have to completely describe the shape. That's draw. That's what we did. We also have to tell our reader what size everything is. And in fact, one thing I think you ought to think of as a caveat, if you did your job right or not, if you walked into any shop and you see some construction guy out there and he's pulling out a scale to measure something on the drawing, you screwed up. They should never have to pull out a scale. We should always give them the complete size description, or what things are. Keep that in mind. That's really what we've done. We've already handled the shape. Now we're going to the size. Now, when we talk about size, we probably ought to define what we're doing. So I've defined dimensioning for you. And this kind of was excerpted out of the text with a couple other statements. So here's really my definition of dimensions. You shall completely describe the size of an object and define the slop allowed for that object during the manufacturing process. Now keep in mind, when we say manufacturing, that's not only in mechanical, that's in architectural, it's in civil, it's in all of these. Because the manufacturing of some object can be digging a ditch. It can be welding a couple items together. It can be a lot of different objects. What do we mean by slop or tolerancy? In essence, we can't build anything to true size. So we have to realize that. You put down a dimension as 3 on an object, it will never be built to 3, ever. Never. I can always measure error in the construction process. Now, should error happen in our labs, in our drafting offices, in our engineering offices? No, we have the technology to be absolutely perfect. So we should be perfect, because there's going to be errors when things leave us. And let's minimize all those errors. Since we have the technology to be, in essence, perfect, we should be. Let's give some more area to the people downstream of us, to where they can make more mistakes, be a little quicker, and we can still get things built correctly. So we have to do that. Not only tell them, but also tell them how much error that they can have. Any questions on that definition? First, let's talk about our units of measure. We're going to focus mostly on machine drafting, although when we do our next course, 135, which really button tails onto this, we're going to go architectural for at least one project, just to kind of mix things up at the end of the semester. Now, for your units of measure, we use decimal inches. Now, the standard from ANSI is when you are doing machine drafting up to 6 feet or 72 inches, you use decimal inches. Decimal inches, not fractional. Okay, that's only the architectural field. So we don't do that. Now, the second thing we do, notice that there is no inch marks on here. None. we do not put units on our drawing. Now, let me quantify that because I said it slightly wrong. We do put units on our drawing, but not with the dimensions. We'll get into that more in a minute. We, in essence, tell them that everything on this drawing is this unit of measure. It's either inches, it's millimeters, it's feet, it's miles, whatever the case might be, and then we do not include our inch marks, our feet marks. We don't put mm for millimeters, we don't put m for meters, we don't do any of that. In essence, we're trying to clean it up and leave it nothing but numbers. So, ANSI standard, decimal inches up to 6 feet. Once you hit that, then you go feet, decimal inches. Okay. 72 inches, if you don't know, is equal to 6 feet. Any questions on that? Okay. How do we come up with our decimal places? Folks, it's really going to be determined by these two things. Thank you, Juan. So when we talk about putting decimals on objects, okay, there's really two things that are doing. Number one, the precision needed to accomplish the need of the part. And I've mentioned this before, but I'll mention it again, and it's kind of a weird statement, but it's a true statement. Folks, whenever we build something, we build it as sloppy as possible, still accomplish the job. Okay? That's really what we're trying to do. Build it as sloppy as possible and still complete the job that the part needs to perform. Okay? So that's one thing. How tight do we have to get the thing to work? Obviously, if I'm building a shovel, I don't have to get very tight. If I'm doing a piston in a car engine, I've got to get very tight. Okay, so it depends on what your job needs to be. Job of the part. The second one, and this is a biggie, machinery environment or the skill of your workforce. Okay, what are they capable of doing? Really, a decade ago, in Twin Falls, I don't know that we could have built to 4 decimal places a decade ago. We certainly have several firms that can get much tighter than that now, because we've had a lot of big firms with pocketbooks that bring in machinery that can do that stuff. But certainly that becomes a huge part. When we get to that, I got a little diagram on the decimal places down below. And let's just really kind of try and drive this point home when we're talking about decimal places. Okay. So if we're dimensioning, keep in mind that if I go 1 decimal point, that's 1/10 of an inch, right? The next one's 100th, then 1,000th, then 10,000th, and then 100,000ths. In essence, that's what those decimal points mean. Now, you ought to also kind of consider that each one of these decimal points really has dollar values attached to them, big dollars. And it's really kind of an inverse relationship. In essence, if I go up to a 1/10, I can do a 1/10 of an inch very easily. I can measure it with a tape measure. I can get somebody ordinarily skilled, probably straight out of high school, and teach them how to get that close in a very short amount of time, 1/10 of an inch, even to 100th of an inch. Keep in mind, a 16th that we deal with all the time, you all can recognize a 16th or an 1/8 now. An 1/8 is the best, it's really a 1/10 of an inch, isn't it? 0.12? It's around a 1/10 of an inch. That's, you can visualize that in your head. A 16th, which is our smallest dimension that we use on our lines, that's what, 600ths? But we can hit those dimensions. And in fact, you'll see even the architectural world, where we're dealing with a lot of wood products, things of that nature, their standard is a 16th for their tolerances, which is half the thickness of a saw blade. Can they hit a 16th? Yeah, they can hit it very good. We've got some framing crews that can get better than a 16th. So keep in mind, that's about the mark though, on that 100th. Right about there is we're leaving the point that humans can do the work. Now, you can do work out to the thousands by hand if you have the right machinery and the person's trained on it, but that person's probably now been through Jim's program or the welding fabrication where they're familiar with lathes, mills, these types of machinery that can get you to that decimal point. Once you get past that, and you start getting out to this 1,000, 10,000, 100,000, I've kind of got some costs where you see the inverse of it. You're getting into some big dollars. Mostly because you have to have machinery and controlled environments to do it. Now, some of you got to mess with Jim's mill the other day when we went in there. Not the injection machine, not the 3D printer, the big one where he made the forms for those. You know, a brand new one of those is over $1 million. So you have to be able to justify spending that much money to build something. It costs a lot of money to put that in. Not to mention also, you've got to start controlling, once you get to here, you've got to start controlling your environment. Which means that your stock material before you work on it has to be set to a certain temperature. You've got to be watching humidity. You've got to be watching vibration. You've got to be watching all this stuff. You can't go out like, K&T Steel doesn't work to that size, but they're a big steel fabricator here in town. They've got a big laydown yard that sits outside. You can't do that here and build to 10,000th of an inch.
What about like the computer micron systems? They're all controlled.
They got indoor, yeah, they got indoor facilities too. I mean, Boeing's probably the best example I've got. There's a reason Boeing's in Reading, Washington. They're in Reading, Washington because they change 10 degrees all year long. That's it. Humidity's constant. That's why they're there, so that they can get away from this. Another thing you've got to watch, I mean, if you've got a machine that's stamping metal on one part of your plant floor, that can affect a machine 100 yards away when you start getting this stuff. So you've got to isolate the footings underneath that. You might have to break the whole building apart to get that vibration away from it. In essence, the point being, we're spending a substantial amount of money to get to here. You hear about these military parts and you kind of shake your head and say, why do they cost so much? Well, this is the reason why. Because it costs a lot of money to do these to the precision we need for an F-35 fighter or a B-1 bomber or whatever the case might be. Space shuttle. I got a cousin who works for Boeing. And she was on a space shuttle deal where they're working on the tiles. They spent $4 million on one screw through development. The one that holds the tiles on the space shuttle.
$1 million?
Yeah, on one screw.
Damn.
And that's just what it costs, but it's pretty important. I mean, if that space shuttle starts coming through the atmosphere and tiles start flying off, we don't have a space shuttle anymore, right? But it's that level of precision that not only in the development, but in the production of those parts that drive some of those costs. And not to mention they're kind of one-time builds, right? You don't build it, mass produce them. So keep in mind, every time you throw a decimal place on here that's unnecessary, you're just tacking on dollars. And really, you're going to get to the point where the thing can't be built. At some point in time, you will. People will just kind of look at you, yeah, right. Can you accept something else? This is kind of a tough thing to grasp in our area because a lot of us grew up in the ag world, right? How many of you have exposure to the ag world? Okay. So you're used to balers, discs, plows, things of that nature. Something breaks, what do? We haul it to the yard, we take the grinder out, we start grinding it, and we put a new piece on there and just kind of, well, use the old all weld, farm weld, I used to call it, stick that goes to everything. And then we're back out in the field and going. And that's a very good way to do it. It's cheap, right? It's cheap because we're not worried about those decimal places. Now, when you get into this stuff, it's a little bit different market. A little bit different. And we've got to kind of realize that and let go of some of our background if you go to an engineering office where this stuff is going on. So keep in mind, we want to, again, build things as sloppy as possible while a part still performs the job it needs to do. Now, when we're doing our drawings, here's your standards for that I would like you to use unless you're told different. if we are doing an English drawing, then you will do that drawing to 2 decimal places. That's the hundredths. And our tolerance or our slop that we will allow somebody is plus or minus 0.02 inches. Or in essence, around a 32nd. This can be built by hand. If we go metric, remember this will be millimeters. You will do them to 0 decimal places. There are no decimal places at all. Your tolerance will be plus or minus 1 millimeter. The millimeter is the base unit for manufacturing in the metric world. So English, all dimensions to 2 decimal places, plus or minus 0.02 inches. Now keep in mind, we won't put inches or millimeters with these numbers or dimensions. Metric, 0 decimal places. I'll wait till I see people quit writing. You got a question, Andy?
No.
Am I good to move forward?
Yes.
Now, since I say we can't do that, we can't put our units with it, I do want to add something to all your drawings from now on. So the unit of measures left off the drawing, but tell the reader in your general notes. So, in essence, general notes. What are they and where do they occur? If I have a drawing, and I'll kind of just sketch our A template. So I'm sitting here like this. Your general notes, if possible, should always sit in the lower right-hand corner. So they should sit down in this zone right here. Now what I want you to put is you're going to put notes. This, you want to use 1/4 inch text. Because it's a title. Now after that, we're going to use 3 notes at a minimum. And now I didn't give myself enough room, so I'll put it down here. So 1. Now, when you use notes, keep in mind that you have to have them all lined up and everything like that. So let me give myself enough room here to put this. So in the lower right-hand corner, so that is your 1/4 inch text. Then we're going to put our general notes. There's the first one. All dimensions plus or minus 0.02 inches. Okay, this is a good note. It tells the reader 2 things. Okay, now, I guess before I do that, maybe what I ought to do is say that all these notes, these will be 1/8 inch text. Okay, so once you get off the title, we go to 1/8 inch text. This note, all dimensions plus or minus 0.02 inches. It does 2 things. 1, it defines the slop of the drawing. The reader knows I take every single number on there and I can successfully make that feature as long as I'm plus or minus 0.02 inches. So in essence, we're giving them 0.04 inches of slop, 0.02 each way, right? Okay, so we're giving them about a 1/16 of slop. Additionally, it tells them the units that we're using. Okay, if we're doing a metric drawing, we will only change this part and we will say plus or minus 1 mm. Okay, that will tell them that all dimensions are metric with the millimeter being base. Plus it's given the tolerance. Now the other thing we need on this, wow, nice too, Pat. Material. We want to list material. So in this case, I put MAT apostrophe L, semicolon, and then CI. Somebody look in the appendix. Did I get these abbreviations right? Remember appendix A1 through A10? Who's got their textbook? If you would, look up material, because this standard changed. It's appendix A1 through A10. That's your ANSI approved editions. That's in your Bertolini text.
Material is
What's material?
MATL.
Thank you. Okay, there it is. What's CI mean?
Cast iron.
There you go.
What?
Cast iron. Folks, use abbreviations. We're going to now start annotating the heck out of our drawings. Get familiar with appendix A1 through A10. That's my point here. Okay. Not that we look this up. Yes, I did. That's the old standard MAT apostrophe L that changed in 1994 or somewhere around there. It's now MATL. So we want material. 3, we want quantity. How many of these things are we making? And you can look that up or not. Quantity is QTY. Now, folks, when you do, yes, sure.
I'm sorry, is that a colon or a semicolon? I think you said.
It's the 2 dot ones. Don't ask me which one that is.
That's the colon.
It's the colon. And I think it's okay if you use a semicolon there too, or a dash, or anything. We need a good separator.